All right, welcome back. We should get going with our next talk. So the next speaker will be Eva Belmont, who will be talking about equivariant homological stability.
Thank you. Yeah, thanks for the invitation. It's an honor to be here at this celebration of Fred's work. Yeah, I'm going to be talking about equivariant homological stability. So this is one of these projects with equivariant in the title, where you take some classical phenomenon, in this case homological stability, and then you introduce a group action. And I think the most interesting kinds of things are when it's not just like, oh, you put a G in front of everything and then you get the same results. But I think the interesting thing is going to be when you get different kinds of structures or different kinds of phenomena. So the classical phenomenon we're going to be talking about is homological stability. And I'll mainly be talking about the configuration spaces kind, but I'm going to give a very general introduction to the kinds of questions people ask. So in general, with this kind of area, you start with a sequence of, let's say, a sequence of spaces, x1, x2, x3, and so on. There are maps between them, and we're just going to call all the maps sigma, even though they're different maps. And the question is, suppose you look at the induced map in homology. So maybe I'll call this the goal, is to show that the induced map in homology by sigma star is an isomorphism for n sufficiently large. And so there's lots and lots of examples in the literature of various kinds of sequences of spaces. So an example might be something like xn is b sigma n. Those satisfy homological stability. That's a theorem of Nakaoka. But there's a whole bunch of results that vaguely have this framework. So given that context, yeah, so I should say my collaborator's name. So this is work with J.D. Quigley and Chase Vogelli. And we wanted to ask, well, what do these kinds of theorems look like when you put a G action in there? So the equivariant version is, maybe xn is a G space for some group. So the groups we've considered are finite abelian groups. Sigma is a G map. And you might expect that, in some nice examples, we might get the same kinds of theorems, that you get some kind of you have a string of maps and you get an isomorphism in homology. But actually, the correct equivariant setup ends up looking a little bit different. So I'm going to call this suggestions. So homological stability isn't like a theorem you prove in general. It's like given specific sequences of spaces might satisfy homological stability. So suggestion for what should a homological stability statement look like in general. And these are inspired by examples. So I'm going to call this goal A. Is maybe one thing you can try to do is prove homological stability of fixed points. And I'm going to leave a blank there so I can come back and fill in something more precise. And another kind of thing you might ask for. So if you're into equivariant spectra or equivariant homotopy theory, the kind of generalization or equivariant version of this sort of setup you might expect is something that involves Berdan homology. So I'm just going to say here something about Berdan homology. And I'll come back and make this more general, but I just want to say a few things here about what is Berdan homology. So if you haven't seen this before, the thing to keep in your head is that it's the correct notion of cellular homology if you're working in the realm of G spaces or GCW complexes. So I can also say it's a functor from G spaces. So at each level, so given an n, it's a functor from G spaces too, and then instead of it being a functor to abelian groups, it's a functor to a more complicated abelian category called Mackey functors. And roughly speaking, what is a Mackey functor? It's an abelian group for every value of for every kind of orbit. So I'll say for every G mod H orbit, and then there's more structure. So it's an abelian gadget that, or it's a yeah, I mean it's an algebraic gadget that's more complicated than an abelian group, and it is kind of indexed by the subgroups of G. So that's what Berdan homology is, and equivariant people feel strongly that this should be the target. You know, if you want to generalize a statement in homology to an equivariant context, it should probably be something about Berdan homology. Okay, so I'm going to come back later and say something more precise here. But the point I want to make up front is that this setup is going to be different from classical kinds of homological stability statements because I'll leave a bunch of room here, a few things to say here. So for both, instead of having a single chain of stabilization maps, the examples lead us towards considering a family of stabilization maps. So instead of sigma, I'm going to index my sigma by G mod H. And instead of just increasing the index by 1, it's going to increase the index by the order of G mod H.
Sorry,
Yep.
blocks the view to the bottom of the board.
Oh, okay, so I shouldn't be doing this. Okay, well, maybe for now, I'll just, is that okay? Okay, thanks. Yeah, so instead of a linear chain of maps, we're going to be considering a more complicated family of maps. Roughly speaking, our results are going to come down to, instead of turning into a sequence of isomorphisms, you're going to get some kind of joint surjectivity. Okay, so what I want to talk about is examples, and in this talk, I'm really going to focus on configuration spaces, and then I'm going to mention, so I want to be more precise about what the target statements A and B are going to look like, and then we have a statement that if you can prove homological stability of the A form, then that implies homological stability of the B form. And the A form is going to be easier to prove. Great. So let's start with my main example is configuration spaces. Okay, so a little notation. So when you talk about configuration spaces, there's an ordered version and an unordered version, and I'm going to put them both on the board, but I'm going to focus on the unordered version.
Well, the statement makes sense.
Okay. All right. So ordered configuration spaces. So let's say the ordered configuration space of n points in a space X is, so I'm going to call this conf n of X, and it's the space of n tuples of points in X and that are all distinct. So such that xi does not equal xj if I does not equal j. And we also care about the unordered version. So I'm going to call that Cn of x. And what you do is you notice that the ordered configuration space has a natural action of the symmetric group that permutes the points. And we're going to mod out by that. So this is the ordered version modulo the action of sigma n. So there are a lot of nice examples. So the most basic one is if I want to look at ordered configurations of 2 points in RK. So this is what happens. So it's pairs of distinct things. I'm going to call this X underline and Y underline. And RK cross RK that are different. And if I want to understand the space up to homotopy, let's think about how I can choose such a pair of points. So for the first point, there's a contractible space of choices. And for the second point, so once I've already chosen a point in RK, I'm allowed to choose any point except for the one I've already chosen. So there are contractively many choices for X, and then an RK minus X worth of choices for the second point. And that's a slightly hand-wavy argument for why this is homotopy equivalent to SK minus 1. Okay, so that's conf. And we can also care about conf 2 of R infinity. So the same kind of argument says that this is S infinity, because infinity minus 1 is infinity. But now, so we can remember this is a contractible space. So it's a contractible space, but with a free C2 action. So this is a model for EC2. And then we have a nice name for what happens when you take the quotient by sigma 2, aka C2. So C2 of R infinity is BC2. Okay, so these configuration spaces are really useful. They come up in a lot of contexts, and they relate to this homological stability discussion because there's a theorem due to McDuff and Siegel that says, so in particular, this theorem is about not just configuration spaces of points in an arbitrary space, but configuration spaces of points in a manifold are particularly well behaved. So let's let M be an open manifold, and to manifold people, open means non-compact. Okay, so in order to talk about homological stability, you need a sequence of spaces. So there is a construction that takes a configuration of n points and turns it into a configuration of n plus 1 points that induces an isomorphism on homology for n greater than or equal to 2D. And because I'm going to want to talk about an equivariant version of this, I want to give a little bit more detail here so I can say a little bit about where this sigma comes from. So if I have a choice of n points, then I'm supposed to come up with a choice of n plus 1 points. So just as a reminder, the Cn thing, you can really think of it as like a subset of size n. So if I start with a manifold. Okay, yeah. So first, so this construction, it's easier to state with a small extra hypothesis. So let's assume that M is homeomorphic to the interior of some other manifold W for W compact. It just makes this construction easier to state. So let's say here's the boundary of my manifold, and like the actual manifold M is inside. And we're going to start with a configuration. Maybe that made it hard to read. I'll just put it underneath. Suppose I'm starting with a configuration of some points, so x1 through xn is an element of Cn of x, Cn of m, and I want to produce another point. So the problem is I can't just say, like, choose my favorite point and then add that to the configuration, because, well, maybe my favorite point was already part of the configuration, and then that will fail this property about the points being distinct. So we have to be a little more creative. So what we do is first add a point in the boundary. And so here's my original configuration down here. But that still doesn't count because this is not a configuration of points in M. The boundary is not part of M. So now what we can do is push the boundary in. So here's the original boundary. I'm going to imagine pushing it. So the dotted line is the image of the old boundary. So I'm just like imagining pushing like this. And so here is this xn plus 1 that's been pushed in. So I'm going to call that xn x prime n plus 1. And then this pushing might also like mess up the points that are near the boundary. So it might have changed my original configuration, but that's okay. So I get a new configuration. And so this x prime, this is an element of Cn plus 1 of m. So the theorem says that, this seems to involve a lot of choices. And the upshot is that the only choice up to homotopy, the only choice it depends on is what boundary component you've used to pick the extra point. So this is a well-defined operation. You choose a boundary component of this containing manifold, and this is telling me how to start with the configuration of n points and obtain a configuration of n plus 1 points. And the theorem of McDuff-Siegel says that this operation induces an isomorphism in homology as long as n is sufficiently large. All right, so that's the classical background. So now is time for the equivariant version. So here we're going to have G as a finite group. And M is a smooth G manifold. So G acts smoothly. I should say open smooth manifold in order to match these hypotheses. Cn of M, I'm just going to say as above. So in particular, M has an action, but when I'm choosing my configurations, I don't have to do anything different. I don't have to choose configurations that respect the action somehow. I'm just choosing any unordered subsets of n points. Okay, so let's have an example. So our motivation for studying these configuration spaces is actually sort of the boring examples of just G representations. So let's look at G equals C2 for the easiest kind of representation. And M is the two-dimensional representation that swaps, it flips about the x-axis. Okay, so just to make sure we know what these definitions mean, an example of an element of C3 of M, it's any 3 points. So I can choose that, and that is an example of a configuration. And there's also an action on this. So this configuration space has an action by G because I can apply G to the points. So if I apply, oh, you know what? I think I like that one, but I want to start with a different one. Let's start with that one. Okay, so if I apply the action to this, so it's going to keep this point on the x-axis, and it's going to flip the other 2 points down here. So I start with one element of the space, I get a different element of that space. That's a G action. So this is the action by the non-trivial element in C2. Now let's do the one I originally drew. So if I start with this, and then I apply the action, well, what the action does is it swaps these 2 points, but I'm considering this as an unordered thing. And so swapping those points doesn't actually change what element of Cn of M you are. And so this is fixed by the action. All right, so yeah, so there are some equivariant configuration spaces, and now we want to mimic this setup. So let's try to add a point on the boundary. And okay, so there are a few things you could try to do here. You could just add a point on the boundary, just pick any point, just like here, pick any point, and try to assert that that depends only on the boundary component. So the different thing here is I really want my stabilization map to be an equivariant map. And if you think a little bit about it, it turns out that if you just add a random point, then that's not going to be an equivariant map. So I don't want to just add a random point. So if I add a fixed point, if there is a fixed point on the boundary and I add it, then I'm going to get an equivariant map. But it turns out that that adding a fixed point on the boundary, if there is one, is a perfectly good stabilization map. But in an equivariant context, we actually want to think a little bit more broadly. So as I'd advertised in the introduction, instead of coming up with a single stabilization map, we're going to try to write down a bunch of stabilization maps that are indexed by the possible orbit types. So essentially, instead of just adding a point on the boundary, what we want to consider is add an orbit on the boundary. And if you want to say well, why don't you just add a fixed point on the boundary and forget about the other ones? Why do we like the other ones? It'll turn out that the best kind of homological stability statement really does involve taking into account all of these maps. Okay, so I can do this in roughly the same way. So this makes sense as long as there exists a G mod H orbit on the boundary of this extra W manifold. So this is a hypothesis. In the same way that existence of W, well, maybe I'll just say that this is a hypothesis, but it does exist in, it does happen in the cases we hear about, which are representations by, or the regular representation. So this is an example of the regular representation. So let's just write down what this looks like. So in the example above, let's take this point. So here's a point in C2 of M. And I can consider two different stabilization maps. So I can try to add a free orbit, or I can try to add a fixed point. And if you're wondering, like, well, where's the boundary? So I want to say that my R2 is R2 with the sign action, or the 1 plus sign action is homeomorphic to D2, and D2, or maybe I should say the interior of D2. So I'm imagining, like, kind of out at infinity. I've got all these points at infinity. Those are the boundary. And some of those points, so the points here and here at infinity, those are fixed points on the boundary. The points everywhere else, basically, those are free orbits on the boundary. So I can, if I want to add a fixed point, what I do is I imagine adding a fixed point at infinity and then kind of squishing everything in. So what that'll end up doing is it'll probably push my original configuration a little bit closer, but then it'll push that fixed point at infinity into some kind of actual fixed point in my manifold. So that's one kind of stabilization. That one adds 1 point. The other thing I can do is imagine adding a free orbit at infinity. So now I'm imagining adding 2 points. I can either think of them as the boundary of D2, or I can think of them as adding 2 points at infinity that are a free orbit. And then I do my construction here, and then I squish that down until I get points that are actually in my manifold. And then these points get kind of squished down as well. So those are the two kinds of stabilization maps that I can do. Oh, I have to be careful about these boards. Let's see, I can erase the top of this. Okay, so the first kind of homological stability statement one might be interested in is about the fixed points. So now let's try to say something about the fixed points. So if I take Cn of M and I take its fixed points, well, these examples up here are like trying to tell you something about what the fixed points look like. So here's a fixed point, and really how you get a fixed point is by picking something that's already a G set. You know, this one isn't a fixed point because the G action takes that set to a different set, but this set is fixed by the G action. And so if we want to find fixed points of Cn of M, we just have to find subsets of size n that actually are G sets. So moreover, there's a decomposition into the type of G set it is. So this right here was an example of a C2 mod E plus C2 mod C2. That's what kind of G set it is. And in general, if I look at G sets of size n, then all I have to, I can break this up into G embeddings of this set into M, and I want it unordered, so I should mod out by the automorphism group. Okay, yeah, so this is just saying every fixed point looks like this for some G set. And we're going to use some notation here. So let's call this CGS of M. So it's fixed points that have that particular orbit decomposition. And given that, so let's simplify a little bit and look at orbit types that are just n copies of a G mod H orbit. So this is picking out n G mod H orbits inside of M is the same thing as picking out n orbits in the part of M that consists of isotropy H. So I've written down some notation here, but this is points in M of isotropy H. So both sides here are saying pick out n different G mod H orbits. If I'm going to do that, then I can just restrict to looking at the part that consists of G mod H orbits. And if I want n of them, I can take n orbits. Okay, so what we've done is if we're interested in the fixed points, then we've reduced a question about the fixed points of something equivariant to a different configuration space. So you can show with some hypotheses that, with some hypotheses on the G manifold, that this thing here satisfies the hypotheses of the McDuff-Siegel theorem. And so this you can reduce homological stability of the fixed points to a classical homological stability statement. Okay, so here.
Is that a definition or a theorem?
Which one? This CGS?
No, that is.
Oh, I mean, I would say it's not a definition. I mean, it's like an easy theorem, maybe. Yeah, like a lemma, maybe. Like maybe you have to think about the point setness a little bit. But the claim is that both sides are saying like pick out n copies, like n different G mod H orbits. Okay, so you observe this, and then you do have to check some hypotheses, state some hypotheses, and check some hypotheses, and reduce to a classical statement. And what you get out is the following thing. So let's assume, let's call this a proposition. Let's assume that sigma G mod H is defined. Remember that requires coming up with a W that actually has the right kinds of fixed points on the, or has the right kinds of orbits on the boundary. And we also want to assume a connectedness hypothesis, that this thing is connected. And then we get an isomorphism on the CGSs. So, yeah, I mean, I would say this thing here is kind of it's a definition. Yeah, it's like suggestive notation. The G is up there to suggest fixed points, but it's a component. Yeah. So the homology of one component to the homology of another component So if I apply sigma g mod h, then I've added g mod h many points. So that's why this goes from S to S plus g mod. Oh, sorry, I guess I don't want to count them. I want to add that orbit. So I've gone from a G set of type S to a G set of type S plus G mod H. And the theorem is that this is an isomorphism if, and then we need a translation of this criterion. It's an isomorphism. Here it says if n is sufficiently larger than the homology degree, and that translates here to saying if, oh, I guess, okay, this is the same as d less than or equal to n over 2. It's easier to state this in terms of d. D is less than or equal to 1/2 times the number of copies of G mod H in S. So it doesn't depend on the size of S. This is only sensitive to the G mod H orbits. And so that's where this bound comes from. Okay, so that is like a homological stability statement. And if we want to take this back to the original question was kind of more general. That's like, what should homological stability statements look like in general if they are true? You know, maybe what I'll say here is, let's assume in the general, I guess I've erased the general setup, but this example, and I think I don't have time to talk about other examples, but there are other examples where you see the splitting behavior. So let's assume that the G fixed points splits up in terms of orbit types. And let's also assume that there exist stabilization maps. Then you want to show that the homology of the component stabilizes. Oops, G mod H is an isomorphism for D sufficiently less than the number of G mod H orbits in S. So I'm just kind of writing down a literal generalization of the kind of theorem we have here. There are also examples of the splitting behavior, say for equivariant classifying spaces. Yep.
So in this M sub H, in this M sub H mod G thing, G doesn't have to act freely on M sub H, does it?
Well, G does, like M sub H is just as a G set, it's a bunch of copies of G mod H.
So G doesn't, but you're dividing by G.
So I'm just saying, instead of like for every G mod H orbit, I'm taking that down to 1 point. So it's like the set of orbits.
I'm just wondering about the topology of M sub H of G. It doesn't look like a manifold.
So I agree, like there is, okay, maybe there is something to think about there in terms of the manifold structure. Maybe, I think I have like 3 minutes. So can I finish this and then we can talk about it later? Okay, so yeah, so that was the first kind of statement. The second kind of statement is we want to say something about Gradan homology. And maybe I'll just squeeze in a comment down here. Oh, maybe, okay, I'm not supposed to write there. Let's write here instead. Okay, so the thing you might expect. So for goal B, you might expect to get a decomposition. So we had a decomposition of the fixed points. Maybe you might expect to get a decomposition of the entire space. So I guess by X, let's say maybe Xn, and like, you know, maybe we might expect something like this, whoops, S, and an isomorphism in Verdon homology. That's similar, but there is no good decomposition, and I think this. So I'm just going to say there does not exist such a decomposition, e.g., for configuration spaces. So if you look at this, like the decomposition for Cn of m, I think is pretty intuitive. You just think about what fixed point should look like. For every fixed point, there's naturally an orbit associated to it. For non-fixed points, like here's a non-fixed point. Like you could like try and be creative and say what orbit does this correspond to? Like I don't know, maybe you complete it into an orbit or something like that. It just doesn't work out very nicely. And so we did try this for a little while, and I think it's just like not the right thing to think about here. And so what we did something different instead. So instead, we're going to reformulate the classical homological stability or part of it as follows. So let's look at the homology of all of the Cn of m's all put together. Then let's look at this as a module over Z adjoin sigma. So now I'm really using this abusive notation by saying the different stable so sigma from x1 to x2, I use the same notation as sigma from x2 to x3. I can think of that as an operator that takes one component of this homology to a different component of this homology. Homological stability is saying, like, or at least the surjectivity part of homological stability is saying, eventually everything is in the image of sigma of something. And so you can say that this is finitely generated as a module over this thing, and then you have to assume some kind of finiteness statement is finitely generated over Z for each n. Okay, so if you reformulate it this way, then there's something we can put here. So the version here is, let's say that, so assumptions, I'm just going to say above plus finiteness. And we want the Verdon homology of all of the xn's to be finitely generated over Z adjoin all of the sigmas. So this is kind of what I mean by joint surjectivity. So that's sort of a general kind of homological stability statement you can prove. There's also a different version. This is like a little bit annoying because it has this finiteness hypothesis that doesn't seem relevant to the stability. So you might also try to get a bound on the connectivity of all of the xn's put together, and then like take this sequential colimit. Let's say sigma g mod h1, sigma g mod h2, and so on. So that might be a slightly more natural kind of statement. So what we have is A implies B for G finite. So the statement A, so we get B is true for configuration spaces because we proved A kind of earlier here. And I'll just say B prime is work in progress. Yeah, so thanks.